Hi, everyone. It's Mr. Vallejo, and this is VRC Chemistry Labs. Today, we are working on 16.2 lesson check on page 531. So let me write that down, 16.2 lesson check, and that is page 531. Okay. We already went over 19, 20, 21 together, but I'm going to write my answers down so that you can see those. Remember what we talked about. How do you calculate molarity of a solution? Molarity, capital M, is equal to the number of moles of solute divided by the volume of the total solution. Okay, so that's number 19. Number 20. Number 20 reads, how does the number of moles of solute before dilution compare with the number of moles of solute after dilution? They are the same. And number 21, we talked about different ways of expressing concentration of a solution as a percent. You could do volume over volume, which was volume of the solute over the total volume of the solution. So the way we abbreviated that was V sub S divided by V total. And you could do the same thing for mass. So that could be mass of a solute or mass of solute divided by mass of solution. So the mass, well, I'll just write that. Mass of the solute divided by mass, total mass of the solution, which we would write M S divided by M total. Okay, so now we're caught up. So that's 19, 20, 21. Let's see what we can do about number 22. All right, reading this for the very first time, let's see what it says. It says, what is the molarity? Capital M question mark. What is the molarity of a solution containing 400 grams? And that is the mass of the solute, 400 grams of copper sulfate in 4.0 liters of solution. So when it says solution, we assume it's aqueous. Just about all chemical reactions that we study are aqueous solutions. You can have an ethanol solution in some cases, but if it wasn't ethanol solution, they would say that. So this is a water solution. So this is an aqueous solution. So V total is going to be 4.00 liters. It looks easy, but it's not as easy as it looks, because what you have to do is, remember, to get molarity over here, molarity is moles of solute over volume of total solute, but we don't have moles of solute. We have instead we have mass of solute. So we have to get from mass to moles. So how are we going to do that? Well, we're going to use molar mass. Well, if it was just an element, we could get that straight off the periodic table. But since it's not an element, it's a compound, we got to figure that out. So what is the molecule is copper sulfate. So in a molecule copper sulfate, you have one copper and you have one sulfur and you have 4 oxygens. Okay, I got that from the molecular formula of the whole compound copper sulfate, CuSO4. All right, so now you might have some of these memorized. Like I know the sulfur is 32, and I know the oxygen is 16. I don't remember copper. I think it's like 55.4, something like that. So I'm going to go to my back of my Pearson book and look at the periodic table. And you probably got it before I do. but what is it? It's 63.546. 63.6 is what it is. Times 63.6. So to work that out, then what you have, and sulfur is 32.06, 32.06, and oxygen 16.0. So that's in case. Oh, you know what? It's a good thing I did that because this is 3 sig fig. This is 3 sig fig. So we really should go to 3 sig fig here. So we'll make that 32.1. Okay. And so when I multiply that all out, I get 63.6. I get 32.1, and 16 times 16 is 32. That's 64. If I add all that together, I get 0.7, and I get 5 plus 4 is 9, and 12 plus 3 is 15, 159.7, 160, right? So that is 159.7 grams per mole. Okay, so now I have the molar. Now I have, what is it? I have the molar mass of copper sulfate, but I only have I have 400 grams of it. So to figure out the molarity is here. Let's write it out. The molarity is going to be, remember, oh, actually, we're not trying to figure out molarity. We're trying to figure out the molar mass of that, and then we're going to calculate it out to get the moles. So I'm trying to get, not molarity, but I'm trying to get moles. But what I would do is I've got 159.7 grams per mole, and I have a sample size of 400 grams. So looking at it, that's going to be, if you had 159, that would be a mole. So it's going to be more than 2 moles of this. So what I have to get the number of moles, it's going to be 400 grams divided by 159.7 grams per mole. And did I get the number of moles? Well, if you look at it, the grams cancel out, and the mole, it's on the bottom of this, so it's going to flip by the time you get the answer. So it's going to be in moles. So we set it up right. And that makes sense from what I just said. So 400 divided by 159.7. Let's see what Siri says. 2.5, 2.50. But that's not the answer. That's not the final answer. That's how many moles we have. And we're trying to figure out molarity. The molarity is moles divided by volume. And we have volume. Now we have moles. So now all we have to do is take this and divide it into that right there, or 2.50 divided by 4. So let's ask Siri again. 2.5 divided by 4. Ah, she says she didn't get that. Oops, here we go. Hang on, Siri. Hey, Siri, 2.5 divided by 4. And so our final answer is 0.625. Okay, so 2.5 divided by 4. And what is this? This is molarity. And I have 2.5 moles. And that is going to be in 4 liters of solution. So my grams per mole is going to be in 0.625. Okay. All right. So that's moles per liter. That's the molarity. So what number was that? That was number 22. And so number 22 looking good. All right. Let's go on to the next one, which is number 23. All right. Number 23. Number 23 says, how many milliliters of a stock solution? So we want volume. What is the volume in milliliters of a stock solution of 2.0 mole, 2.00 molar KNO3 potassium nitrate? Would you need to prepare 100 milliliters of 0.150 molar KNO3 potassium nitrate? Okay, so hopefully you were able to read that in your own book on page 531. What you see is how many milliliters of stock solution would you need? So we're trying to figure out the initial volume that you need. But what is given is a molarity of 2.00 m. And we also have in the final solution, what would you need to prepare 100 milliliters? And so this is going to be the second volume, 100 milliliters of 0.150 molar KNO3. So the molarity, the second molarity is 0.150 molar. I'll remind you that what we figured out was that M1V1 equals M2V2. So we have M1V1 equals M2V2. What we don't have is V1. So we want to solve for that V1 by dividing both sides by M over 1. So that's our solution right there. So now we're going to take M2, which is this one right here, 0.150 M, multiply it times V2, which is 100 milliliters, divide that all by M1, which is 2.00 M, and then that's going to be our answer in, because these cancel, milliliters. Okay, so let's get that answer. All right. 0.15 times 100 divided by 2. Okay, so the answer is 7.5 milliliters. Okay, so that is the answer and the solution to number 23, 7.5. But if you'll notice, there's 3 sig figs all the way across. So I've got to change that to 7.50 milliliters with a box that. Ta-da, that's number 23. Okay, we're doing 22, 23. Let's do 24 through 26. Here's number 24. Number 24, how many moles of solute are present in 50 milliliters of 0.2 m KNO3? So we want moles of solute. That's what we're looking for. In 50 milliliters, that is a volume. 50 milliliters, 50.0 milliliters of 0.20 m. So the molarity is 0.20 m. 2 sig fig, 3 sig fig are answers, and 2 sig fig. Well, remember that what you have is molarity is equal to moles of solvent over the volume of the total volume of the solution. So what we want is moles of solvent. To get this all by itself, algebraically, all you have to do is multiply both sides by V total. that cancels. The volume of the solution is canceled there, but we need to multiply it on this side also. So now we have moles of solute equals molarity times volume total volume of the solution. All right, that's what we wanted, moles of solute here. So now we plug in. M is 0.20 M. Volume was 50.0 ml. Okay. And then what you get is multiplying that out. Let's do a visual so that you can see it, even though my buttons are a little goofy today. 0.2. Yeah, there's an air bubble underneath that. So 0.2 clear. 0.2 times 50 equals 10, which is 10. See, remember M means moles per liter. And over here we have milliliters though. So milliliters, we really should have converted this from milliliters to liters before we did that. In order to get rid of this milliliter, and it looks better when we do it by dimensional analysis, remember that the conversion factor for milliliters and liters is there are 1,000 milliliters in 1 liter. Okay, so we divide this by 1,000. You get the answer is 0.012 sig fig, 0.01 moles per liter now, right? And so moles per liter is a capital M. So there is our answer. Oh, wait, we were going for moles, weren't we? We were going for moles. See, these cancel out. And then here's the milliliter canceling out. And then here you have liters over here. What did I miss? Oh, all right. Let's take this and spread it out, and you get 0.20 moles per liter, and you get, by dimensional analysis, you get 50 milliliters. Well, those don't cancel, but we know that there are 1,000 milliliters in 1 liter. So now you can see things cancel out. There's the milliliters, there's the liters, and then we have moles, which is where I goofed, and that's number 24. And so that's the answer, moles of KNO3. So my cancellation of units was a little goofy, and that is why we got the numerical part of the answer is correct, but I had to go back because my units were goofed up. So we wanted moles to begin with. So now we have moles at the end because these guys were able to cancel out. All right, that's number 24. Oh, that was the answer. So let's box that. Okay. And there we go. That's that. Let's go to number 25. 25 is, what is the concentration in percent of a solution containing 50 milliliters of, so you want to know the concentration in percent VV. So percent VV, V over V. Okay, that's what we're trying to get. and you have 50 milliliters of diethyl ether in 2.5 liters of solution. So let's say you've got 50 milliliters of C4H10O, and then you have 2.5 liters total solution. So we'll say solution. Now again, you have milliliters and liters, so you've got to convert this. Remember, 100 is 0.1 liters, so 50 is going to be 0.05 liters. So we would take 0.05 and divide it by 2.5. Okay, so again, we could just show you. If we want to convert this to liters, then we have 50 milliliters, and the conversion factor is 1,000 milliliters in 1 liter. Then that'll give us the top value of 50 divided by 1,000. And there it is, like I said, 0.05. So now you're going to take this 0.05 and you're going to divide that by 2.5. So let's do that. That equals 0.02. Okay. And so because this is a percentage, I got to move this over to the right too, or you can multiply it by 100. So 0.02 divided, or not divided, times 100 equals 2. Remember, it's just a percentage, so you got to move over twice. So that's going to be 2%. Now it's 2 sig fig, so I'll say 2.0%. And if I look at the answer, woo, that is it. 2.0% of what? Diethyl ether, which is C4H10O. And so that's the answer in volume to volume. Actually, that should be before this here. So you stick that right there. That'd be the way you write it. That's number 25. Woo. And then the last one is number 26. The last calculation it is. Anyway, what mass of K2SO4, so you're looking for mass, would you need to prepare? Okay, so this is the mass of the solute. What's the mass of the solute? And it's potassium sulfate. What's the mass of K2SO4 would you need to prepare 1,500 grams? And so that's a mass. 1,500 grams of, and this is the 1,500 grams of the total solution. Okay. And also the last thing they tell you is that the 5% solution. Okay. Now, because it's a 5% solution, we know that it is 5 grams of the solute, which again is K2SO4. And that's going to be 5 grams of solvent. Because it's a percent, it's going to be in 100 grams of the total solution. So we have that, all right? And so because we have that, we know that what we have to do is multiply the mass by this conversion factor, because what we're looking for is mass of the solvent. So this is mass of the solvent. Same thing. I'll write it like this, K2SO4. So it's easier to see what we have. So what's given is it's 1,500 grams of total solution. So we have 1,500 grams of that. Okay. And then we have this already. And we have 100 grams of solution. And then we have, so this is the total solution. This is total solution. So these G's are going to cancel out. And then we have 5G of K2SO4. So to calculate that one out, all you got to do is, oh, you can't see some of that. There it is, right. Let's see. It's a little better now. You have 1,500 grams times this, which we got from, it's just a 5% solution. It's 5 into 100. So that's what that is. And that becomes a conversion factor for us. So we can calculate the percent by mass with the conversion factor here. So now we just need to multiply these things together. 1,500 times 5, and then divide it by 100. And that gives us an answer of 75. So what we have is 75, and what is this? This is grams of K2SO4. And our, okay, let's see, is that right? 75, yeah, 75 grams of K2SO4. And that's number 26. And let me box that so that we know that that's our answer. And then your work is shown for number 26. The last one we have is, what information would you need in order to convert molarity to percent by volume? Well, I mean, you can just look at the definitions of those. For molarity, and this is number 27. For molarity, you need moles of the solvent divided by total volume of the total solution. Okay, we'll call that V total. All right, in order to get number 27, in order to get percent by volume, what you need is, and it's percent by volume, what you need to know is the volume of the solute, and you need the volume of the total solution. Okay, so you would need to know the molecular mass and density of the solute. You would need to know those in order to convert the moles of the solute right there to the volume of the solute. So you need to get from there to there. In order to get from there to there, you need to know, again, the molar mass. And you remember we calculated that out in a previous one in number 22. So that's how we calculate the molar mass. And then another factor you would need is density. And density is abbreviated with the Greek letter rho. And that the formula for density, I'll do dot dot. The formula for density equals mass over volume. So if you knew the density and you knew the molar mass, you can go from moles of solute to volume. Okay, because there's the volume. And if you knew this number, density, which is intrinsic, which doesn't change for each chemical. I mean, within a chemical, depending independent of how much you have, that density is going to stay the same. So if you had this number and you had this number, then you could figure out mass. From that mass, if you know the molar mass, you can figure out, you can convert over to volume of the solvent. No, solute, sorry. So what is the answer to that one, number 27? Molar mass and density then. If you knew those two things, then you would be able to do it. I wasn't even going to do that one, but I did it. So there you go. Density, oh, and I didn't write it, and molar mass. Molar mass, which you calculate with the information, with info from the periodic table. All right. Ta-da! That's what you did. We're all done. Quad erat demonstrandum, which means that this is what we set out to do. And we finished the second problem set all together. You and me together, we're done. So now we have both problem sets done that were in our learning program. If I take a look at, hey, shh. All right, let's go. Let's go to back to screen share and go back one more time to Canvas. Let's see. Is that it? Got a video playing. I didn't even know. What is that? Ooh. All right.